All right, folks, today we're going to do nuclear podcast number 5. It talks about fission, fusion, and nuclear reactors. All right, first we need to look at a couple of definitions. The first is fission. And fission means something breaking apart or one thing becoming two. So if we look at this particular rock over here, we can see that this rock is actually split in half right here. So there's a fissure, S-S-U-R-E. There is a fissure in the rock. And so that's how do you remember that this is fission. It is two things breaking apart. All right, now fission, the concept of fission is we can take uranium-235 and hit it with a neutron. And when we hit it with a neutron, it becomes uranium-236. That neutron goes in there, but then we have an unstable nucleus. We've talked about how these things are unstable. Well, instead of giving off an alpha particle or a beta particle or something like that, it actually splits kind of sort of in half, where it puts krypton, which is number 36 protons, and barium, which has 56 protons. It splits into those two things, plus it gives off 3 additional neutrons and a whole bunch of energy. This is called nuclear fission, and this is what we use to power nuclear reactors. Right? Again, this is fission, breaking apart. So this is Lisa Meitner, and she concluded that the uranium nucleus had split during the reaction, producing barium as one of its barium nucleus as one of its elements. And element 109 is actually named after her because she came up with this concept. Now the nuclei would violently repel each other. They would push each other completely away. Well, why is this? Why do nuclei repel each other? Of course, because they're both positively charged. Okay, so they repel each other. So these things fly apart pretty quickly, right? And she figured out that this violent repulsion could be a source of tremendous energy, right? Energy. Why? Where is this coming from? Well, this is if these things are moving quickly, then we have speed. And if we have speed, we have temperature. So when these things split apart, they generate a lot of heat. So she called this a nuclear fission reaction. We just shorten it to just fission because that's typically what we call it, is just fission. Okay. The reaction also produces more neutrons than it absorbs. All right. So let's go back and look at this again where we have a neutron. That's a 0 down there. Right. And we're hitting uranium-235, which is number 92. Right. And it produces U-236, which is only there momentarily until it breaks apart again. Now when it breaks apart, it goes into barium, which is number 56, and 141. And it produces 92 and 36 krypton. But what's interesting here is it also produces 3 neutrons. All right? And neutrons have no charge, but they do have mass. So I'm adding 3 of them in to get up to 236. Right? Well, what happens when we do that? Well, these 3 neutrons come right back over here and hit more uranium, which generates more neutrons, and then these neutrons hit more uranium. Okay? So we call this a chain reaction. Right? Now, in this case, we're only going to 2 levels, but think of it as going to 3. It's the same concept. It just gets bigger, quicker, right? Where the neutron over here goes and hits a nucleus, and it spawns 2 more, or in our case, it was 3 more, and then it just keeps going. So what would something like this look like to the naked eye if it was completely uncontrolled? Because most chain reactions, if you think of a chain reaction, it would be uncontrolled. 1 produces 2, 2 produces 4, 4 produces 8. Or in our case, 1 produced 3, 3 produced 9, 9 produced 27. What's it look like to the naked eye? Well, what it looks like is a nuclear bomb. And if we don't control it, that's exactly what's going to happen. So what we have to make sure, if we're going to do this in a nuclear power plant, we sure as heck don't want a nuclear bomb. So we need to control it much better than that. All right. So if we look at fission reactions, we do not conserve mass. Remember, some of the mass disappears. Now, most of it is still there. We're watching most of it, and we can track most of it. But remember, when you get beta particles coming off and alpha particles coming off and that kind of thing, we have some mass which is being converted to energy. And this is where we go to Albert Einstein and his equation of E equals mc squared. Our energy is in joules, our mass is in kilograms, and the speed of light is 3 times 10 to the 8th meters per second. You multiply that, especially when you take this bottom number and you square it, all right? This gives us a huge amount of energy for the small amount of mass that we convert, right? Now, we do this all the time in nuclear power plants, right? So if you lived next to one, would you be concerned that this thing might blow up? Well, you know, obviously that is a concern, right? And you have to think about that, right? Now, in a nuclear reactor, there is not enough uranium-235 to sustain a runaway chain reaction. In other words, to make a bomb. Now, could it burn? Yes. Could it get extremely hot? Yes. Could it create a major disaster? Yes. Is it a nuclear bomb? No. Okay. So, the uranium that we use in a nuclear reactor only contains about 3% uranium-235, where bombs contain over 90%. And if you're listening to the news, if you're one of those people who listens to the news, you'll hear something about enriched uranium. Okay? The enriched uranium is this stuff. It's the 90% U-235. The non-enriched uranium is what we would use in a power plant, which is only about 3% uranium-235. So let's look at when we go and we take uranium-238, which is what we normally use, and we add a neutron, what happens? Well, it makes U-239, which makes neptunium and also produces a beta particle, which means we're getting some heat as well. All right. Now, what happens when we hit uranium-235? We make U-236, and what we saw was that we have fission going on, because this is a fission product. These have broken apart into barium and krypton, and we have a lot more neutrons, and those neutrons go back and they feed these reactions. Okay, so if we have enough U-235 there, we're potentially going to have a chain reaction. And in fact, the second reaction is a chain reaction, but in a nuclear plant, we're going to control it. Now, how do we control it? Well, we have control rods. We're going to show you a picture of what control rods look like in a minute. But they absorb neutrons. So they're often made out of graphite, as in carbon. Sometimes they're made out of silver, right? But the concept is their purpose is to absorb neutrons, right? Because we have to absorb some of these neutrons. If we don't absorb these neutrons over here, we got a problem, all right? So somehow we have to absorb them, right? So we're going to absorb them with graphite, silver, other materials that we use, right? So what could possibly happen in a nuclear reactor? There'll be a problem. I'm sure there are fail-safe mechanisms in there, and there are. There are many redundant systems, but there are a few things that could mess us up. The biggest one is human error. And when you look at the 3 Mile Island thing, which we're going to do in a little while, human error is a big piece of it. All right. Now the problem is that human error, when you combine it with mechanical failure, you have a major problem. And that's exactly what happened at 3 Mile Island. You had human error, you had mechanical failure, you had both going on, right? The other major concern that we have is radioactive waste. That's RAD. How about I just do waste? All right, radioactive waste is a huge problem, right? And just kind of one more thing you might want to think about is we have thermal problems because we heat up water. Nuclear reactors generate a lot of heat, and they make water hot. And so we're going to talk about that in just a minute. All right, what we have is the way a reactor works is very similar to the way any kind of electricity generating system works. Right? We have some coolant down here. We have some liquid. Let's just say it's water coming in through the bottom. Right? And the water comes in and it touches all of these uranium things. They're very hot. They're generating lots of energy. They're generating a lot of radioactivity. This water is radioactive, right? So that water then comes up and it gets hot and it turns to steam and it comes out here, right? Now these control rods can be lowered into here to absorb more neutrons or not absorb as many, and as a result they can control the speed of the reactions that are going on here, right? What happens is this water is getting hot and then we can take that water and we can put it into here. Right? And what it does is it heats up another set of water. Right? Now this could be water, it could be some other thing like sodium or something, but anyway, it's some mechanism that's liquid, and it goes through here getting very hot, and it takes this water and it heats it up. Now you'll notice these waters never touch. And the reason for that is they want to keep all of the radioactivity in this yellow part, and the purple water is not radioactive. So this yellow water or whatever comes through here, and it heats up the water, which then turns to steam. The purple steam then comes up here and it turns a turbine and goes into here, and when it comes into here, we have another pump that's pushing water through that makes this steam cool down. So in other words, there's lots of pressure. There's high pressure over here, and over here there's low pressure because you're converting the steam back into water. Right? So that water goes through the pump and then gets recycled and gets heated up again, and we have high pressure going to low pressure, and it turns a turbine which generates electricity. Now, it is interesting, we're going and putting in water at about 27 degrees, right, which is essentially room temperature, and when we output it, it's slightly over 100 degrees Fahrenheit. So what happens when you take this water out of a river or out of a lake and put it back into the river or the lake, and it's 100 degrees Fahrenheit? Well, certainly it's going to warm up the lake. And if you're up at Lake Anna, up in Northern Virginia, they have a nuclear power plant on the lake. That lake never freezes. Guess why? Right? At least it never freezes near the nuclear reactor because the nuclear reactor is keeping that water so warm. Right? And you've seen pictures of Lake Anna in previous podcasts and previous units. So this is the way that that a nuclear reactor works. So you can think of this as in a normal coal-fired plant, you're just heating up this steam, you're heating up the water into steam with a boiler, meaning you've got fire burning under here, like a coal-fired plant, and it generates the steam and it goes through this same process. The only difference is how you get it heated up, and that's what this thing is doing, this nuclear part. And all of the nuclear radiation is contained in this containment shell so that the radiation does not get out. If that containment shell ever breaks, well, then you have radiation leakage, right? And we'll talk about that when we talk about what happened in Japan. So here we have a picture of 3 Mile Island. Now, you're actually going to watch this, this PBS video that's up here, and you're going to do that a little bit later when this podcast is over. But you'll notice we're sitting by water. And the whole purpose is they take water in, they bring water in, and they cool the reactors. These are the reactors over here. They cool the reactors, and then they push the water right back out again. So the water is coming in at about 60 or 70 degrees, and it's going out at 100 degrees. So it's going out a lot hotter than it came in. Right, again, this is the thing you're going to see. The pink part is the reactor we just talked about. Here are your control rods, and we heat up the water into steam. It comes through, it turns a turbine, and then it gets cool again. Your cooling water is what you're using pumping in and out of the river, and then it just repeats that cycle over and over. All right, so 3 Mile Island in 1979, that was an almost major disaster that was just barely averted. The 3 Mile Island core temperatures, again, you're going to watch this video later, they reached over 4,300 degrees Celsius. Now, had they gone just a little bit higher, the core would have completely melted, and we would have had a huge problem because the core melts, it goes down, hits the water table. When it hits the water table, you have a major explosion because of all the pressure from the steam that comes out, and your entire containment area just blows completely, right? Thinking of where this is, we would have had major radiation contamination to places like Philadelphia and New York. Right? So that would have been a huge problem. There are a total of 110 nuclear reactors in the United States, 2 of them in Virginia. One is at Lake Anna, and one is at Surrey over towards the coast. Now, there was another major disaster, which is Chernobyl. That happened in 1986. You're going to watch a movie called Chernobyl Heart. It's a documentary. C-H-E-R-N-O-B-Y-L, Heart. And that's a documentary you'll be watching to learn about what happened in the Ukraine, and it was near Russia and Belarus, and they're the people who took all of the the mess from it because that's where the fallout went to. Contaminated hundreds of square miles, created numerous birth defects and cancers. There is no exact number of how many people died from this. There are under 100 people who died almost immediately, but then you get into the thousands of people who have died since then because of cancers that they can't say, well, this was definitely related to Chernobyl, but chances are it was. In 2011, there was a crisis in Japan when there was a tsunami and an earthquake, and it melted down one of the reactors, and it leaked 6 million pounds of radioactive water into the ocean, which, by the way, came over to the United States. So we detected the radiation all the way over here in the United States. Here in Japan was the problem, and as you can see, that radiation went everywhere all throughout the Pacific. Okay, bunches of people died, etc., etc. So they have all of these issues with radiation. Right. One question that we have is, what do we do with nuclear waste? Well, the concept was we were going to ship it all by railroad car, by truck, over to Yucca Mountain, which is in Nevada. They've since changed their mind and said that's not going to happen. So if you look, for example, at this pool of water, which is all blue, it's actually glowing. The stuff that's in here are the spent nuclear fuel that is not generating enough power now to be useful, but it certainly is still generating power and will for thousands of years. And they just have it sitting in big vats of water to contain the heat and to contain the nuclear material that's being generated, the beta particles, alpha particles, etc., that's being generated. So there's another concept which is called fusion. Right? Fusion is the opposite of fission. If you think of fusion, bones are sometimes fused together, so they're held together, like you see over here. Well, fusion is putting things together. It's the opposite of fission. So the same thing is true when we look at chemical reactions, where we have two small nuclei which form together, join together to form a large nucleus. All right? So like fission, fusion converts some of the mass of the original nuclei into energy. Again, it's a very small amount, so we don't actually track it in our reactions. But for example, we can say hydrogen, this is deuterium, plus tritium. Remember, tritium is radioactive. We put it together and we get helium, or an alpha particle, plus 1 neutron. All right? Neither of which are pollution. So this is one way that we can make fusion happen. Now, the problem is fusion is very difficult to produce and control. Why? Because obviously, when you look at these things here, they're both positive. You've got hydrogen nuclei, they don't want to be together, so you have to whack them together to make them happen. Right? So they repel each other. But the problem is, the good thing is there's no waste here. All right? We don't have a lot of nuclear material that's left lying around somewhere. So how do we overcome this repulsion? Well, we have to whack them together really, really, really hard. All right? And the way we do that is we create something called plasma. All right? So what does plasma do? All right? Plasma strips off the electron cloud, so we only have protons and neutrons. So we have stripped off the electron cloud. We have high speeds and high temperatures. High speed and high temperature. Our high temperature is around 40 million Kelvin. Now, that number is higher than anything I can imagine, but the problem is it melts anything it touches. It's just too hot. So how can we actually put this? I mean, it's not like you can put this on a pan on the stove. How do you actually do this? Well, you have to keep all of this separate, and you do it because it's all positive. You can isolate it in a magnetic field. If you have positive charges all around it, and the thing in the middle is positive, it's all being repelled, and it's going to stay in the middle. And that's exactly what they do to overcome the repulsion. Right? Now, the problem is, these are called thermonuclear reactions, and it's the energy produced by the sun. It's also energy produced by hydrogen bombs. Now, the first one is the equation we just wrote down a minute ago, but here's another one, which I'm not going to write again, but notice we have 4, and these are normal hydrogens, and they come together to produce a normal helium plus Let's see, what is a positive thing? Oh, well, remember that is a positron. Okay, we actually produce 2 of them. Okay, so we produce 2 of those. All right. So, we have tried to do cold fusion. Cold fusion didn't work. Right? Here we put out a positron. We also put out some gamma radiation here. This is put out by the sun. So if you look at the sun, one of the things that they have a problem with our spacecraft that are up in orbit around the sun, around the Earth, is that they don't have the protection from the gamma particles that we do here that are that all of our air produces for us. So they have more problems with radiation poisoning. The astronauts do. Right? So all of this is what's going on in the sun. Okay. All right. So let's kind of wrap up here. Fission is what we use for generating nuclear power and for generating radioactive isotopes. We do not have the technology yet to use fusion safely. So what we use for radioactive power is fission. All right. Now, we have 2 things that you have to watch. One of them is the PBS activity on 3 Mile Island. So look at your worksheet for that, or just go on Blackboard and there's a link under this unit that will take you to the 3 Mile Island activity. There's also another link that will take you to Chernobyl Heart. It's a documentary. This is a 45-minute documentary. The PBS activity will take you 5 minutes. All right, but the documentary on Chernobyl Heart is a 45-minute movie. You should watch that because there will be questions on the test about it. All right. And then there's a PBS NewsHour video, which is, I think, 11 minutes, all right, which there's also a link to. You don't absolutely have to watch that, but it shows you what has happened since in Chernobyl. And it talks about cities like Pripyat, which are completely deserted. They're ghost towns. There's nothing there. The buildings are still there. The stuff that was in them is still there, but there is nobody living in that area at all. All right. That is it. We're done. If you have questions, please see us in class. Sorry these are so long, but we're almost done. You're in the home stretch now. See you in class. Have a good one. Bye-bye.